Amherst, Chemical Engineering, Polymer Science, 757, Polymer Rheology, Professor H. Henning, Winter, Lecture 2A. There's another interesting phenomenon which I want to discuss with you. And again, the polymer, the macromolecular material, is in between the classical liquid and the classical solid. And this phenomenon is the so-called slip phenomenon. It describes the interaction of the polymeric material with a surface, like in channel flows or in all processing machines. You have a polymer next to a metal surface, for instance, and you want to know what's the interaction. And here I sketched a graph in front of me. The polymer, when, for instance, pushed through a channel, it is sometimes sliding along the wall. It's not at zero velocity or at the velocity of the wall. There's a jump in the velocity. If you would have a solid sitting on a wall and you push that solid, it would go from zero velocity to the full velocity immediately. But in our case, in the liquid, we have the jump of velocity, and then on top of that, the liquid is deforming, so it's also in between. Now, in a pressure flow, we have stationary surfaces and push the liquid through this, or in a drag flow where two surfaces, a quiescent surface and a moving surface, are in relative motion. There, the slip occurs, of course, and both surfaces. And that has tremendous implications. Let's go back to capillary flow, which we studied last time, a typical flow in polymer processing, where a polymer is pushed through a die, and along this wall, there might be some slipping. And it can be detected very easily by measuring the flow rate of that system versus the pressure drop. Here it's already normalized, and we will talk about the shear rate, but this is basically the flow rate, and this is the pressure drop in the capillary. Now, in a polymeric liquid which behaves normally, there is no specific occurrence. You can measure this curve at small capillaries and large capillaries and renormalize this. By the way, you have this figure at the end of the first stack which you got. This is the information of flow phenomena. Now, we measured the pressure drop flow rate relation for a filled system. And there you see a strong radius dependence. As soon as the liquid starts to slip, there is a contribution to the throughput, and you see that in the experiment very nicely. Vinogradov and his co-workers in Moscow looked at this slipping phenomenon with polymers of high molecular weight, and they picked very narrow distributed polymeric materials. And for those, they found that there's just a threshold. There's a specific shear stress at the wall above which the polymer starts to slide. And if you extrude or push the polymer through a capillary at lower stress levels, it will stick to the wall and will behave quite normally. A commercially interesting material where this phenomenon occurs regularly is the linear polyethylene, the high-density polyethylene. And I'm going to show some old measurements of Uhland in '79, where he built a die, a round die in this case, and mounted some pressure transducers on it and some temperature sensors. And then he pushed at a certain rate it was actually a plunger on the upstream here of this capillary, so in a capillary rheometer configuration, he pushed polymer through here, and then he measured the pressure drop. At low rates, there was nothing specific. He had just normal response for pressure, shear rate, and temperature in the system. But when he went to high throughputs, like you would look for in production, then he found that the polymer starts to pulse. It doesn't come out continuously. It somehow sticks to the wall for a while and flows regularly, and then starts to slip again and pushes out very rapidly, and then it goes very slowly again. A stick-slip phenomenon an instability which is induced by this interaction with the surface. You can see that when the pressure goes up very high, it builds up during a sticking operation, and then there's a rapid discharge of this capillary rheometer, and the pressure goes down, and at the same time here you see viscous dissipation, you see heating effects on those thermocouples. Always when you have slipping, you see all the energy which is used for pushing the polymer through the capillary is converted into thermal energy, and you can pick that up with a thermal sensor near the wall, and then the thermal sensor goes up and down the same way as the extradate. The extradate itself is regular at low rates. This is again our flow rate versus pressure drop curve in some normalized fashion. So at low rates, this relation is quite normal. At higher pressures, you get higher rates. But then when you exceed a certain stress level, it starts to pulse back and forth. That's where we have this irregular pressure profiles before. And the extradate has a smooth region and then some distorted region and a smooth region. That's called bambooing, because the extradate really looks like bamboo. Here the sections are equally in length, but very often this is just a very short section, and then this is very, very long. And the extradate is useless for any commercial purposes in this case. But now comes the interesting phenomenon. When you go to even higher pressures, when you operate up here, then suddenly this pulsing disappears. It's unstable all the time, but it's only unstable in a very thin layer near the surface. Let me go into Ulan's paper. I think he has a picture somewhere. The extradate looks fairly nice. Here, this is the extradate. It's not distorted very much, and the surface is not perfect, but it's okay. And indeed, that's the operating condition which is used for producing the 1-gallon milk bottle. The plastic milk bottle, which you all know you can buy in the supermarket, is produced at as fast as possible, at a rate as high as possible, and it's operated at this unstable condition. So the surface is not too bad. Now, when increasing the rate further, then the extradate looks something like this. It's all distorted, and it's a bulk instability phenomenon which occurs out here. And most likely that's a different type of instability. It comes from the inlet in the die, and then there are some periodic vortices at the inlet, and so it's all unstable also, but for different reasons, and it's actually very difficult to analyze those unstable flows. The slip phenomenon, which I just talked about, could occur really between the polymer and the metal at the interface directly, or the polymer could be modified in a very thin layer near the wall due to the high stresses. Maybe molecules can be aligned, or some changes occur in the polymeric material. And under those conditions, it's not perfect, not ideal slip really at this interface, but it's like a lubrication phenomenon. And we would have a hard time distinguishing one from the other. So this is as much as I want to talk about the slip phenomenon. I have one more interesting phenomenon, and it's quite appropriate in the year where the Columbus anniversary is. There's a saying that ships go faster in the Sargasso Sea. You know, the Columbus was not just going straight west to go to America. His discovery was that he had to go south first and then go west, because the winds were more favorable. And when he went over, he hit the Gulf Stream in the region south of Florida or Cuba, and the water looked real mucky. The sailors were scared anyway, sailing away from Europe. And on top of that, the water got worse and worse and worse, and they were really afraid that they would get stuck in this type of mucky water with lots of algae. But effectively, their ships were going faster with algae in the water. And the phenomenon is called drag reduction. And here I show you a simple version of that drag reduction. It's associated with flow through a pipe. The flow rate, F, yeah, we have the flow rate given by the average velocity. This describes or defines the Reynolds number in this case. Here, and then the pressure drop in this case is given by F, by the friction factor. So the friction factor in laminar flow at low rates is quite normal for water, and for water which is a little bit mucky, where you have a few macromolecules added to that system. However, when the flow rate is increased, when you go to higher rates, the flow becomes turbulent, classical fluid mechanics. So you know about that. But somehow the turbulence is changed when having macromolecules added. There are only few macromolecules added. The laminar flow is not changed. Viscosity is not changed noticeably. But certainly the turbulent flow is changed in the sense that it needs less energy for that turbulent flow. And then viscous dissipation is reduced. And in case of Columbus ships, they just could go faster with the same power coming from their sails. And this phenomenon is used by firemen sufficiently. They have a pump, and sometimes the water pump is too small to squirt fast or far enough into a fire. They have to move very close. But if they add some polymer to the water, and they do this quite often, then they squirt further with the same pump. They call it vapid water. Also, it's used in some cities with sewer, for instance, sewer problem. If you take a very flat city like San Jose or so, if there's lots of waterfall, there's not enough tilt to discharge all the rainfall. In this case, polymer can be added, small amounts, to the sewer, and with the given inclination, small inclination in the city, you have sufficient discharge and you avoid flooding. So there are interesting applications. There are military, people thought that there would be military applications. You could, for instance, have this in your ship, and when you see the enemy behind you, or it depends whether you are fleeing or whether you want to attack. Anyway, if you want to go faster, you discharge the polymer around your ship and you go faster. The problem is that the other guy has also the same polymer, and the question is who has more of that material and can go for a longer time. Eventually, it would be a peaceful navy, because you would not have any room for ammunition on your ship anymore. You only would carry polymer to go high speed. Yes?
Are you going to define what the symbols are for like friction factor, etc.?
The question is, what's the definition of the friction factor, and other symbols I'm using here, shear stress and gamma dot wall. Answer is yes, I will define those in detail. We will talk about capillary rheometry, and then we talk about those flows in detail. The friction factor is probably not appearing again, because it can be defined nicely for the Newtonian liquid, but for polymeric liquids, it's not as meaningful. And it's not as meaningful because we are operating at low Reynolds numbers where the flow is laminar, and then it's the whole problem is different, and we will present the data differently, not in terms of the friction factor. But so for the friction factor, I would recommend standard texts in classical fluid mechanics to look at that. I think we should take a short break, because I want to switch to a new subject here. So if Becky is here and can stop. Yes? Oh, she gives me I don't know, should I continue? She wants me to continue. We have to have enough tape on the second. Okay, so this was leftover from last time. Let's move to the next subject. We have to define basic concepts to be clear about the language we are using. And this is the overview which you have. It's on sheet 1 of all everything. So we will move to chapter 2, basic concepts, and we'll look at the strain. And the subject is really the definition of strain tensors. We have to find a mathematical formulation to capture a strain. And that mathematical formulation then can be used to analyze our experiments. And most likely it will be a very simple mathematical formulation which we are going to use. And then we use that mathematical formulation for the strain to formulate constitutive equations. That would be to describe the stress in terms of strain and strain rates and all of those details. Now, how can we capture a deformation mathematically? How do we do that? Let's start out with a few observations which make it easy for you to define strain tensors. So you basically could do that yourself after having seen those. And then we will talk about the so-called deformation gradient tensor, which comes naturally, but I won't say more about that. Then talk about strain tensors in general and rate of strain, how fast do we deform the material. And then we reduce everything to look at specific flows. And as soon as we do that, everything reduces to something very, very simple again. It's complicated in some mathematical contributions in intermediate states, but then it will be very simple. So how can we observe strain? One possibility would be, as sketched down here, imagine you have a lump of clay, and you're deforming this clay. How do you know that you're deforming this piece of clay? You know that you deform it by observing the external shape of that lump, and you would say if the external shape goes from this to that, or you probably would make something nicer, some cup or some different geometry, you would say you're deforming this material. So the external shape is a measure of deformation. Now, if your material would be transparent, like clay is not transparent, but if it would be maybe a piece of silicone, then you could imagine that you draw some lines in this material. I just drew some red lines, and then when deforming this material, those lines would stretch, and they would change their angles, and they would get curved. Right? That would be also a measure of deformation, which we would use to characterize, to quantify the deformation in this case. So let's go. Let's explore that a little further, and I brought an experiment here, which I want to do with you. It's a balloon which has all kinds of things written on, but see, those are the lines here. If you see the lines here, they have an angle. And now when I blow up this balloon, I'm deforming it. Okay? So the deformation let's write this down. For the balloon, the strain can be observed by us. We're saying the radius r prime goes to some new radius r, and in most cases, in this case, the new radius is larger because I'm blowing up. But if I release the stress, or if we release the air, then it will go down. So we are following the deformation of this balloon. Now, the stress, or let's say the pressure in that balloon would be given in terms of the pressure. Now, what determines the pressure in that balloon? Let's draw a cross-section through this balloon. It has a skin, something like this, which is curved. So this is the skin of this balloon, and we have an interior pressure, and this pressure is pushing the upper half of the balloon up and the lower half of this balloon down. And what keeps the balloon together? Now, that's a stress acting on the skin of this balloon all around. So let's write down a force balance in this case. The stress on the skin times the area it's acting on. This is the circumference. 2 pi r times the thickness of this skin. Let's call it h. So that's holding the two halves of the balloon together. And this is equal to the force pushing it apart. And that force is equal to the pressure times the area pi r squared of that balloon, right? Now we can rewrite this and find that the pressure is equal to the stress in the skin. R is canceling, pi is canceling, so we have 2h divided by r, and this is the force in this balloon. And you can see that as when the balloon gets bigger, the pressure is smaller, is reduced, assuming that the stress is about the same. Of course, if you have more tension in that skin, it might be increasing. So with R increasing, we have less curvature, and you see that in this force balance. Yes?
I don't get it. Are you talking about half long?
I'm talking about 1/2 of this balloon, and I'm doing a force balance on this 1/2. And the pressure pushes it up, and the pressure is acting on the projected area, which is pi r squared, and the force pulling it down is coming from the skin. Okay? And now comes the point I want to make. The pressure in my balloon, note that I'm walking. The pressure in the balloon is independent of me walking. It just depends on the radius of this balloon. And I'm also rotating, or I'm rotating the balloon. The pressure in the balloon is independent of the rotation. So in this experiment, we are, to come to a conclusion here, if I draw this down here on the bottom of this sheet, the motion which we introduce by blowing up the balloon and by walking and rotating, this motion involves a rigid displacement. The balloon is translated and rotated, and it involves a strain, the increasing in size of that balloon. And only the strain is giving rise to stress in their system, not the translation and not the rotation. Now, this is with a balloon. That's a very simple example. But you can generalize that. A fluid flowing through a capillary. Initially, I had this example for a material flowing through a capillary through a dye. Now, a material element flowing, excuse me, a material element flowing through this capillary is clearly translating, and it is also rotating, and it is deforming while it flows through that. And only the deformation gives rise to stress. And when we analyze the flow field, we have to separate all those components. And that will be an objective in the further work we are doing. Now, just to set the language right, we have to introduce a few details. The first detail is the continuum assumption. We will treat the material as a continuum. That means we ignore the fact that the material is discontinuous on a molecular scale, and not only on a molecular scale. In polymeric systems, you might have two-phase structures like in a blend or in a block copolymer, where jumps in properties occur on 100 or 1,000 angstrom level, on very large scale. Now, those scales might be achieved in an experimental conditions, and our flow channel might be small enough that you violate the continuum assumption. So we have to be very careful, and we have to come back to the continuum assumption when talking about multi-phase systems. even a macromolecule is in the order of 100 angstrom in size. So our flow channel might be very small, and we might violate this assumption, this continuity assumption. In spite of this, in most cases, for one thing, we don't know better in most cases, and also for many applications, the continuum assumption holds. So in many derivations, we will just assume that the properties continue to zero volume. We just include those limits, or zero area. We will use this in our derivations. Question?
Is the assumption still valid?
In which case?
Composites, fiberglass and carbon fiber.
In composites, it is valid. let's say you have, the question is about the validity of this assumption here with composites. And certainly, if you have a fiber-filled system, you have, say, large objects in a continuous matrix. Now, if your flow channel is much larger than the size of your particles, your filler particles, then the continuum assumption is okay. If you want to describe the flow in the vicinity of these fibers, you have to renormalize your approach. You might take a macroscopic model for the overall flow, and then have another model which is on the scale of your fiber, and then you have to splice those together. It's very, very complicated. So the continuum assumption is not easily used in those composite applications. Here, I applied the continuum assumption to the density. We could say a material element having a certain mass dm has a density dm over dv, and we would define the density as the limit as this material element goes to a very small size. That's just one example where we could use this continuum assumption. Let's move further. The continuum now is assumed to consist of point particles. It's a contradiction in itself. But it means that that within the structure of it means that within the material, let me draw it means that we could define a material, say a lump of material. If you're, Becky, if you please focus on the blackboard. Yeah, thanks. We could now pick a specific point of this material, and we could assign a certain position. Let's say we have an observer, stationary observer, delta 1, a Cartesian coordinate system, delta 2, and delta 3. And we could assign a position of this point here, and then we could pick another point B, say here, and we would define the deformation of the material by drawing now a plane in there in this material, or a line. In this case, I draw a material line A connecting the point, let's say material vector A, connecting point A and B. Now, this is assumed to be a line. This black line here is a line which consists of material points. And a stretching of the material would deform this line, would make it longer, would make bend it. We could stretch it and flip it over, like making a pizza or so. You would describe the deformation of this material by picking certain points of this material, and those we would call material points. And we also could maybe put a plane through that material element, and on this plane there are material points, and this plane, whatever happens to it, if we again stretch it and flip it over, for instance, that plane would be then a three-dimensional surface, and it would always consist of the same material particles. Now, an intersect of two of those material planes would give rise to a line. And if we talk about two planes, it would be a straight line, or if it's three-dimensional surfaces, then it would be just a line in space, and that would be a material line which we will try to describe mathematically to describe deformations. Now, the state of a material would be the agglomeration of all the points here, all the points of these material elements. If you know their mathematical description, know their location mathematically, then you would say you know the state of the material at time t. So this would be state t, or let's take this as t prime, and then when deforming this material, you would generate some other, here at some later times, you would have state t prime. And that means that the points in this material element change their relative position. So you would have now maybe A here and B there. And this vector, which connects the two, would be A here, and here we would call it, say, A prime. So that's what we mean with state. And a change in state, a change of the position of our material points, or relative position of those material points, would be called a deformation or a strain. Now, it's called a deformation or strain if only two states are involved. But if this material element keeps deforming, keeps flowing through a channel and changes its shape continuously, then a continuous sequence of states is involved, and that we would call a flow. Okay? So when looking at two states for now, we don't exclude flow. We will just use the same concept later on for many states, and then see the evolution of the shape of a material element, and then discuss the flowing of polymeric material. Now, purposely, I discussed material. I discussed a case where we deform this material to a very large extent, and then flip it over, and we would get some curvature. Those lines would not stay as straight lines. But mathematically, that would make everything very, very complicated. We would be lost very soon in a jungle of equations. So how can we formulate a complicated deformation in an easy fashion? And we will do that by using the so-called locally homogeneous strain. And this is described on this sheet here in front of me. We first would say a strain is homogeneous. That means the strain is the same throughout the entire material. Whatever part of a material you pick, it's subjected to the same deformation. So that's a homogeneous strain. And in that case of homogeneous strain, a straight material line, as drawn on the blackboard, will remain straight during the deformation, and also a plane, not a versus crooked surface, I mean a plane in that material element will remain plane during the entire deformation. That's the definition of a homogeneous strain. And now comes our simplification, which doesn't really reduce the results which we will deriving. It's just saying that for any flow, we will be able to take a material element that is so small that within that material element, the deformation is linear. And that we will call an infinitesimal material element. And the strain we will describe for that element will be homogeneous. And we can apply that approach now to macroscopically inhomogeneous deformations, inhomogeneous strains, by just saying locally at this position we have a homogeneous strain of that type, or in a strain rate of that type, and somewhere else in our macroscopic, in our large material section, somewhere else, the strain is different. So with that type of notation, the strain becomes a point function in our material. At every point, we can assign the same. We can assign a strain and a strain rate. And that's quite interesting. Before that, I used not a point, I used a line or used a surface for describing strains, right? So we use a concept of observing lines in planes in a deforming surface, in a deforming material, and we're extending this concept now by applying it to every point individually. And we're talking about an infinitesimal material element, infinitesimal line, which remains straight during the deformation, and infinitesimal material plane, and all this. And then we can treat non-homogeneous flows. Let's take a break here, and then find agreement here. I picked the right position now. Chemical Engineering 757, Polymer Rheology, Professor H.H. Winter, Lecture 2B. Now let's put the system to work. Let's look for mathematical formulation. And again, we will start very easily with a simple experiment. The mathematics we really need will result in a deformation gradient tensor. That's what I want to build up with you. Now, let's assume that we have a rubber band and it has an initial length like this, and then we are stretching it to a new length. The length change is given by L prime resulting into L by this deformation. And we could take a small line now in this deforming material. We would have delta x prime in the beginning, and due to deformation, we get delta x. The stretching is given by the macroscopic stretch. So L prime over L is equal to delta x prime over delta x. And we could rewrite this. That's the formulation I will use in the next one. We could say delta x prime is equal to f times delta x. And everything is scalar in this case. F would be the stretch given by the length change by the macroscopic length change. So that's the 1D picture, which is kind of obvious. Let's go to the 3D picture, where a material element is following a path line, say in a flow through a capillary. And we would pick two states from doing that deformation, a state T prime and T. We would take a little material element, say at T prime here. This would be the first one. And T then at some later state. And again, the deformation will be described now with a material line, dx, a small material, an infinitesimal material line, because we talk about an inhomogeneous flow. So an infinitesimal material line, dx prime at the early state and dx at the later state. Now, from before, we know that the motion of this material element incorporates a strain that will change this line here, but also translation and rotation. Now, when we describe this material line with a vector, then the position of that vector, whether you have a vector here or there, does not matter in its mathematical formulation. A vector is defined by its magnitude and by its direction, but it will not tell us where this material element is. So when looking at dx prime going to dx, we were talking about a length change and an angle change. This line is rotating. And that's what I wrote down here. I would say dx prime is going into dx. This is the new vector. And mathematically, you can, you can transfer one vector into another by multiplying it with a tensor, f. And we have to put some meaning to this f. But at this point, this is just the definition of f, and f is called the deformation gradient tensor, and dx is just the material line at two states. So what is df? And I will spend the rest of the lecture on df and even a little bit more. Now, we could say that that f is a differential operator. And let me go back to the picture on the wall, and let me erase our notation here, and let's just say that this is our delta x, our infinitesimal vector at the state t prime, and this is our infinitesimal vector at the current state t. And actually, I put t prime here. This goes from t prime to t. Sorry about this. So when deforming our material, we are deforming this little line. But now let's look at it differently. Let's say we are sitting at point A, and point A is associated with a path, maybe with a path going along like this. And every point in this material element is associated with a path. Right? That's the part of the flow field we are looking at. So if we move away from A by some increment, we will define a new path, and associated with this new path is a new position over in our old material element. So by just going a step delta x here, now I have to be careful here with my lines, we are looking at a new path which is associated with delta x prime. The motion defines those two states uniquely. So you can go back and forth. Both states are on an equal footing. And we can treat now the relation between dx prime and dx as a differential operator. And that's what I'm going to do. I lost my nice little pointer. Okay, so we would say dx prime here in the first state has three components in a coordinate system. And each of those components in 1, 2, or 3 direction depends on the choice in the second state t prime. So let's take the ith component. Dx prime I is given by dx prime as it changes with x1, multiplied with dx1, and its change in x2 direction multiplied with dx2, and its change in 3 direction multiplied with dx3. And if you compare now this equation with our previous equation, which we had here, this was our defining equation for the relation between dx prime and dx, then you could immediately say that f is given as the differential of here dx prime with respect to dx. Now, look at the subscripts. I have subscripts ij, and I put the first subscript with the differential operator and the second subscript with the x prime. Larson does it the same way. Other people are mixing it up. They're rotating it. And I prefer to have the sequence as we are writing the sequence down. It's more consistent when doing it this way. So just you might not even notice it, but sometimes it might cause trouble that the notation is reversed. Now, what do we expect from F? What properties will we expect? We already touched it somewhat. F describes the translation or the transformation from the state T prime to state T of a line. And this line is stretching and rotating, but the translation is not described by that. So F contains only, from our motion, remember motion was deformation or strain, plus translation and rotation. And now we don't have the translation included anymore. F gives us only the rotation and the deformation, or the length change of this material vector. And so it's already going in the right direction. We want to get rid of translation and rotation if we want to, for the purpose of calculating the stress. In general terms, now we could say that F relates an infinitesimal material vector at two states, say state prime and state without prime. And I'm using this type of formulation here and in the following. So far about the properties. Now let's do some calculations with that. And here it's, if you even increase a little further, magnify further. Becky, please, yes, okay, good. I didn't magnify it enough. Now this is a sketch somewhat like drawn on the blackboard. We are deforming a material from state T prime. This is the lower part of the state. Let me have a nicer, let me go to this point again. So our material element is subjected to a strain from state T prime to state T. I will denote the strain by F, because F is characterizing the strain, and that's what we would like to formulate mathematically. But in the moment, let's assume we know that. Let's say we have all the components of the strain. And the theorem goes something like this. It says, if we know A1, A2, and A3 in the prime state, and we also know this at the later state T, then we can calculate the relation between any force vector. We would call that force vector, say, R prime, as it transforms from R prime to R. So all the A's, all the black material vectors are given, and we want to relate R prime and R, want to see whether this works. Let's get started with the relation of the A1, A2, A3 vectors. So given is the set of this vector at state T prime, state T, and clearly those are related by, say, A prime 1 is equal to A1 times F. This was the deformation we had before. And A2 prime is equal to A2 times F, and also with a third vector. And F is really relating those. So if we know A1 and A2, A3 at those two states, we can calculate F. We can determine the components of F when doing that. That's one aspect, and let's just leave that for the time being. Let's look at a second argument. We could decompose now this vector R prime into three components. We could express R prime in a little segment in direction of A1 prime, plus a little segment in A2 prime, plus a segment in A3 prime, right? So those three vectors don't have to be orthogonal or orthonormal to each other. We just take segments of any of those three vectors, and we would express R prime in terms of those three vectors, a sum of three vectors. And now those vectors are material vectors. Say we take a fraction, let's say we take half of A3 prime to describe R. Okay? And then when we deform the material into the new state, how much would we have along A3? Again, would be half. Right? So the fraction of the vectors of A1, of A2, A3 vectors do not change when we deform the material. Therefore, the front factor, R1, R2, R3, is the same in the new state. It's also R1, R2, R3. It's not changing. So we are already using the concept of material vectors to formulate this relation. Okay, so this is our vector R prime. And within R prime, we can replace now A1 prime with the formula for you can magnify a little further. It's too small here. Yes, thanks. So we replace A1 prime with A1 times F, and we put this over into this position. Yeah, we would put this up here. We would insert it here, and we would get the new formulation R prime is equal to R1, our same coefficient, times A1 times F, the same one we do for A2 times F, A3 times F, and F is factorized in all three cases, so we can put this outside, and we get R prime is equal to this vector times F, and it's really equal to, I left something out here. This is times F, and this is really equal to R. So R prime is equal to R times F. Or in other words, we can show that we don't need any more information. The information was complete, the information we had before, by just defining those three vectors, A1, A2, A3. Therefore, the conclusion is, if you know F for a strain between T prime and T, you have a complete definition. You don't need any more. F gives a complete complete description of the deformation from state T prime to T. And that's why we could, for instance, say, go from here, it's just F between T prime and T. That's a complete description of this deformation. To simplify things, let's look at specific flows. We already had looked at the so-called shear flow. In shear flow, we take a little cube, a little material element, and deform it. We would have a cube at some state T prime and deform it by angle alpha. And the tangent of this angle alpha is equal to gamma. That would be the shear strain. The shear flow of this type, let me draw a picture. Again, we would maybe look at the flow through a capillary. Would have a velocity distribution, something like this, would be U1, and a material element would move along a certain radial position. Here this would be, say, X, and this would be some radius R. So material element would move along here, but a material element has a finite size, so we could take a cube, say at some state, and then at a later state, this cube will be deformed because the velocity is higher on the bottom of that cube than on the top, and the material element will be sheared, has some angle like this. And in this case, the angle is negative. It doesn't matter whether you have positive or negative angle in shear flow. So that type of flow, which is common to many applications, that's the type of flow we are looking here. The velocity distribution is described in the top here. This is the velocity increases linearly with the distance from, say, the bottom of your material element to the top. And we could write down a velocity field saying we have a flow in one direction, which is changing as we move up in two direction. And the moving up is given by the shear rate, gamma dot, is equal to the velocity gradient. So the distance R2 times velocity gradient gives us the new velocity. While a velocity sideways, say in two direction or three direction, is constant. Or in most cases, the velocity sideways is 0. In this application, which I drew on the blackboard, the velocity is 0. Any questions? Now, for that velocity field, we could define a velocity gradient. You could look at the velocity at one position and compare it with the velocity at some position, some distance away. And that would be higher or lower, and it's really defined by the local velocity gradient times the distance. So we need the velocity gradient for defining the velocity field. And we can pick now any material vector for formulating our deformation gradient. Let's pick the diagonal of the cube. Let's pick R prime being just the diagonal. It would have a unit vector in one direction and two direction and three direction initially. And then as this little cube is deformed, the vector is elongated. It has more in one direction, it's longer. In two direction, it stays the same. And in three direction, it stays also the same. Now we can calculate this. And in general terms, it goes something like this. Vector R prime at the early state is given as this. It's a material vector. And the point in one end of this vector has, say, velocity u0. And at some increment later, some time delta t, it will be at this new position here. And the top of this material vector moves at the velocity u0 times the velocity gradient times the distance. And if we take this velocity of the top multiplied with delta t, we come to the new position after some time delta t. So our R prime vector will be transferred into R prime plus delta R prime after an increment of time, like this. And if we go really over long distance, we would integrate, and I showed this here, the new vector R is given by the old vector R prime, corresponding to this, times an integral, here, the integral over the velocity field. And for the velocity gradient, we can put in the components up here. And then we find that R1 is equal to the old R1 plus the distance here times gamma, and R2 and R3 are staying the same. So that would be a typical calculation. You will see that in different contexts. Again, I will go through this when doing further calculations. Now, the total deformation is given by this angle alpha, which is we take the tangent of this angle, and that will give us gamma. Gamma is the shear strain as an integral over the shear rate from t prime to t. And if we now take our, we start out with R prime. This is those are our initial components. And we end up with R. Those are the new components. Then you can rearrange that and find the deformation gradient tensor. And it has the components 1, 1, 1. And it has gamma on the off diagonal. And inversion of that matrix gives you something similar, but it has minus gamma here in this case. And you can check, you can multiply those two and find that consistency would tell you that this is equal to 1. Reduces to the unit tensor. I will do more calculations of that with you. So if you just have the basic concept that we draw material lines and follow their components, then that's good enough for the moment. Now let me apply it again now. Let's look at deformation, which is a little simpler to imagine. It's a stretching deformation, and it's an extension. We would pick a little cube of material again, and we would stretch it into a sheet. We would make it long and flat. We could stretch it, say, in 2 directions. And then it would increase in size in 1 direction, maybe increase in size in 3 directions, and would shrink in 2 directions just for conservation of mass. Something like this is necessary. And to describe this type of deformation, we take a velocity field. Say the cube is moving with the velocity u0, and the stretching is given by the velocity gradient in the material, epsilon dot 1, epsilon dot 2, epsilon dot 3, and the basic kinematics now is given with those velocity components. We have a velocity gradient which describes the stretching. You can picture this in the following way. You could say this little cube here is stretching because the front end of this cube is moving faster than the back end. So it's stretching out in time. Or in this case, the bottom is moving more slowly than the tops, and it is being squished together. So somehow the velocity on the bottom and the top has to be different. If you would say this is at rest, this corner, then the top would have a negative velocity, and the further you move away, the larger this top velocity is, and the front here is moving at some positive velocity away from this origin, from this corner. And that's described in the velocity gradient. The velocity gradient having 4 components, a stretching component in 1 direction, 2 direction, and 3 direction. And our material vector now originally has the components R1, R2, R3. This would be the unit for the cube, would be the unit components. They would be all 1 and would be multiplied with the unit vector in 1 direction, 2 direction, and 3 direction. And at some later time t, those are given again by vectors in the same direction. The direction hasn't changed. This vector and that vector, they are collinear. They have the same direction, no angle change. But their length change is given as a stretch. And that stretch is defined here. Here. Say R1 is equal to R1 prime times L1 times the stretching in 1 direction. And we do this for all 3 components. So we have either a positive stretching or negative stretching, depending whether it gets longer in 1 direction, 2 direction, 3 direction. And the total stretch is given as an integral over the stretching over the entire past. Yeah.
Where does that come out from the exponential term?
It comes out from the question was why we get the exponential form of this case compared to shearing, right, where we took the straight integral. You have to describe this, say in a one-dimensional example. You could say that the length of of a fiber which you are going to subject to stretching flow. This length is increasing with time. So at some later time, we would say L of t is bigger than L0. And the extension rate, if we assign a velocity field, say u1 is equal to 0, and we have u1 is equal to epsilon dot times L. That's the type of kinematics we were looking at. One corner of our material element was at rest, and the other corner was moving because there was a velocity gradient in our material. Okay, so this extension rate is defined by the change of length of this material element divided by the instantaneous length of the material. That's the definition of the extension rate. And if you integrate this, you will find that L of t, you get the logarithm when you integrate this. You would have epsilon dot dt is equal to dl over L. You get the log coming in, and then you integrate this, and you find that the solution is equal to L0 times e to the epsilon t. If this is really at t equals 0, and this is at some finite t. Now here I assumed a constant rate. A constant extension rate. And if you don't assume a constant extension rate, you will find that this one is given as an integral over all the extension rates in time. And this is where this integral is coming in. So if you integrate for variable epsilon dot, then you have L of t is equal to L0 times e, or let's call it exponent now, of an integral from 0 to t of epsilon dot t double prime dt double prime. And we would do this for the example I have here. We would do that in one direction, we would do that in two direction and three direction, and that would give then the formula here for the stretch. And now with the formula for the stretch, the L1, L2, L3, which we calculated here, we can calculate F. It's just 1 over L1, 1 over L2, 1 over L3 on the diagonal, in no off-diagonal terms, because we don't change any angle. We picked a coordinate system collinear with the corners of that extensional flow, and then there's no angle change. F is only has diagonal terms, and it reduces to that simple format. So to bring this to conclusion, what we discussed today, we do small material lines into a deforming material. Small means that we look at lines which stay straight during the deformation. If you would have a long line in the material, would be curved, would be folded during a deformation. So we introduced the concept of a locally homogeneous flow, and we are observing the length change of a material line, and we are observing the rotation of that material line. and we're using that for defining strain. But so far, in that concept, we have rotation and deformation included. We excluded translation, which we don't want to have. And the next step now will be the exclusion of the rotation. The question is, how can we separate rotation and strain from that formalism? And you will see that's quite straightforward. And then we will come back to the examples of shear and extension, and the formalism will reduce even further. We will do that next time.